In the previous video, we covered the definitions for low-piled storage of Class 1 through 4 and Group A plastics. High-piled storage applies whenever we exceed those height limits. In this video, we will review the design requirements to protect high-piled, palletized, and solid-piled storage using CMDA, CMSA, and ESFR sprinklers. When we refer to CMDA sprinklers, we are simply talking about standard spray sprinklers. However, NFPA 13 specifically uses that designation within storage chapters. There are 3 core rules for CMDA sprinklers that we must keep in mind. These rules serve as the foundation for our design, applying to all storage categories across the board, from palletized and solid-piled to rack and shelf storage. First is the relationship between the sprinkler's K-factor and the minimum required density. As we reviewed in the density video, to address the concern of producing small water droplets that lack sufficient downward momentum, the standard sets a minimum acceptable K-factor based on the required design density. Where a density of 0.2 gallons per minute per square foot or less is needed, the K-factor must be a minimum of 5.6. For situations requiring a density greater than 0.2 and up to 0.34, the K-factor must be 8 or larger. Finally, if our hazard requires a density greater than 0.34 gallons per minute per square foot, we are required to use sprinklers with a K-factor of 11.2 or larger. Moving on to our second rule, we must look at the response type of the sprinkler itself. For CMDA storage applications, standard response sprinklers are our baseline. We can only use quick response spray sprinklers if they are specifically listed for that exact storage use. Why do we have this strict limitation? It comes down to how storage fires behave. Often, a sprinkler system will successfully establish control over a storage fire, but the fire will continue to burn and release a massive amount of heat until the fire department arrives for final extinguishment. Because quick response sprinklers are highly sensitive to heat, there is a real danger that this sustained heat release will trigger additional sprinklers far away from the actual fire. If too many of these remote sprinklers activate, the increased water flow through the piping creates higher pressure loss. This leaves less pressure available for the sprinklers near the fire's origin, resulting in less water discharging directly over the fire. Therefore, we cannot simply swap standard response and quick response sprinklers interchangeably, and we must always verify that our quick response sprinklers are explicitly listed for the storage scenario we are protecting. Our third rule for CMDA sprinklers addresses a special allowance regarding temperature ratings and design densities. In most cases, the design density associated with a high temperature rating is less than that of an ordinary temperature rating. However, when using an ordinary or intermediate temperature sprinkler with a K-factor of 11.2 or larger, the standard allows us to apply the more efficient density criteria originally designed for high-temperature sprinklers. To understand why, let us look at early fire tests. Originally, high-temperature K5.6 and K8 sprinklers were used to limit the number of open heads, which conserved our water and allowed for lower design densities. However, later tests revealed that ordinary temperature K11.2 and larger sprinklers perform even better. Their increased droplet size and downward momentum provide superior fire control. Therefore, we are permitted to apply those efficient high-temperature densities when using our larger ordinary or intermediate temperature sprinklers. To find the hydraulic calculation criteria for Class 1 through 4 commodities in palletized and solid-piled arrangements, we must first determine whether the commodity is non-encapsulated or encapsulated. For non-encapsulated commodities, our design path is straightforward. We can protect palletized and solid-piled storage up to 30 feet in height by simply referencing Table 21.2.2.11. This table outlines the required densities for both high and ordinary temperature sprinklers based on our storage height and commodity class. However, when dealing with encapsulated commodities, our height limits and rules become much stricter. If the encapsulated storage is 15 feet or less, we can still use that same table. But when our storage exceeds 15 feet up to a strict maximum of 20 feet, we fall under special criteria. In this specific height range, we must use sprinklers with a K factor of 11.2 or larger. Our required densities also shift: 0.46 for Class 1, 0.53 for Class 2, and 0.6 gallons per minute per square foot for Classes 3 and 4. If our encapsulated storage exceeds 20 feet in height, we are strictly prohibited from using these CMDA rules. Additionally, we must note that across all of these conditions, regardless of encapsulation, our minimum design area is always 2,000 square feet. Before we leave this section, we must highlight a few interesting details regarding the table. First, in most cases, the densities required for high-temperature sprinklers are lower than those for ordinary temperature sprinklers. We have already reviewed the reason for this. Second, as storage height increases, the required density also rises. A primary factor that makes storage fires particularly challenging is the immense fuel load, typically expressed as the total mass of combustible material per unit of floor area. Few occupancies possess fuel loads as extreme as those found in storage facilities. In these environments, commodities are frequently stacked to the ceiling, heavily concentrating the combustibles and ultimately creating highly demanding fire scenarios for us to manage. Consequently, to counter the risks of taller storage, we generally require a greater volume of water to discharge from our sprinklers. Third, we find that in certain situations, for example, a storage height of more than 20 and up to 22 feet for Class 4 commodities, the minimum required density for an ordinary temperature rating is 0.43 gallons per minute per square foot. We know from our earlier rules that for a density this high, we must use sprinklers with a K factor of 11.2 or larger. But we also know that when using these larger sprinklers, our rules allow us to use the lower density required for high-temperature sprinklers. This begs the question, when the use of high-temperature sprinkler density is permitted and that density leads to a more optimized system design, why does the table also list the density for ordinary temperature-rated sprinklers? In older editions of NFPA 13, there were no requirements linking density to K factor. Therefore, some of our existing systems use a lower K factor for densities exceeding 0.34 gallons per minute per square foot. Thus, retaining these values in the table helps us evaluate those existing systems. To achieve fire control for plastics, we utilize the NFPA 13 decision tree. Navigating this systematic chart allows us to accurately determine our minimum required design density. We have already covered many of these terms in our commodity classes videos. For example, we know that protecting Group B or free-flowing Group A plastics is treated similarly to Class 4 and Group C is similar to Class 3. We also previously defined expanded and non-expanded plastics, as well as cartoned and exposed configurations. Now we will explore some of the new terminology introduced in this chart, such as unstable, stable, and solid unit loads. Pile stability can significantly affect the required density for our system. As we evaluate the structural integrity of the stored goods, we must remember that gauging this relies heavily on professional judgment. Surprisingly, an unstable stack can actually work to our advantage. When these piles collapse early in a fire, the fallen material limits oxygen flow, and it also converts a highly combustible vertical arrangement into a flatter horizontal configuration. Because hot gases are less dense and naturally buoyant, they rush upward, causing vertical fuel loads to burn much faster. when an unstable pile collapses. It disrupts this rapid vertical fire growth. While a flimsy pile is clearly unstable and a heavily strapped pile is distinctly stable, most of our commodities fall somewhere in between. Because a stable pile requires a more demanding sprinkler design, we take the more conservative approach. We always assume a pile is stable unless we are absolutely certain it is unstable. Finally, the term solid unit load is defined as a single object with no hollow center or open air spaces. Because a fire on a solid unit load can only burn along its exterior surface, combustion is severely limited by the lack of oxygen. However, true solid unit loads are incredibly rare. We must be very careful to apply this classification only when an object strictly meets this exact definition. Now that we understand the decision tree logic, we will apply it to our system design. Every unique path on the flowchart corresponds to a specific column designation in tables 2133A and 2133B, which define the minimum required density as a function of the maximum storage height and ceiling height. Table 2133A provides these parameters in imperial units, while Table 2133B provides them in metric equivalents. For example, if our goal is to protect Group A expanded plastic that is exposed, stable, and solid piled, with a storage height of 15 feet in a facility with a ceiling height of 30 feet, we begin with our decision tree. This tool guides us directly to column B. From there, we consult Table 2133A. By evaluating both the storage height and the ceiling height, we determine our minimum required density, which is 0.9 gallons per minute per square foot. It is worth noting that Section 21332 permits the interpolation of density between listed storage heights. This allowance helps to optimize our system demand. If, in our example, the storage height changes to 13 feet, we can determine the exact density required rather than conservatively defaulting to the more demanding 15-foot storage requirements. To achieve this, we look at the design densities for the nearest listed heights above and below our actual storage height. In our example, the required density for a 12-foot storage height is 0.8, and for a 15-foot storage height, it is 0.9 gallons per minute per square foot. Next, we calculate the difference between these two benchmark densities. This 0.1 gallons per minute per square foot difference is distributed over a 3-foot span in storage height, meaning the density changes by 0.033 per foot of height difference. Since our actual storage height of 13 feet is exactly 1 foot higher than the lower limit, we simply add this 0.033 gallons per minute per square foot increment to our base 0.8 density. By doing so, we calculate a precisely optimized required design density of 0.833 gallons per minute per square foot. As we explored in our density video, the decision tree and corresponding tables help us gauge the relative fire severity among different plastics. When we examine the tables, we observe that for any given row, the lowest required density is consistently found in column A. By referencing the decision tree, we see that column A is dedicated to non-expanded, unstable plastics, as well as non-expanded, stable, solid unit loads. This indicates that these specific Group A plastics present the lowest relative fire hazard, as they require a lower density of water for effective protection. We already discussed the reasons behind this earlier in this video and in our video on commodity classes. To perform our hydraulic calculations, we naturally need both the discharge density and the design area. While we just explored how to determine the required density, the design area follows its own specific set of rules. In most cases, our baseline minimum design area is established at 2,500 square feet. However, we have two notable exceptions where this area can be safely reduced. The first exception applies to closed arrays, where we are permitted to reduce our design area down to 2,000 square feet. A closed array is defined as a storage configuration with flue spaces of 6 inches or less. These restricted flue spaces limit air movement deep within the pile, starving the fire of oxygen and allowing us to effectively control the hazard with a smaller design area. However, we must exercise extreme caution before relying on this reduction. Closed arrays are very difficult to maintain in active day-to-day warehouse operations. If forklift operators set loads down even slightly more than 6 inches apart, the array is no longer considered closed, and our carefully calculated sprinkler discharge might suddenly become inadequate. Therefore, unless we can absolutely guarantee that the loads will always remain tightly packed, we should design our system safely assuming an open array. Regarding the flue space, it's important to note that it has two different effects on a fire. On the one hand, narrow flue spaces of less than 6 inches help restrict oxygen and choke the fire. On the other hand, these narrow spaces make it difficult for water discharged from our sprinklers to reach the fire origin. Therefore, NFPA 13 takes two different approaches based on our storage method. In rack storage, we rely on maintaining flue spaces of at least 6 inches to help ceiling sprinklers activate faster and to allow discharge water to reach the fire more easily. If we cannot maintain these flue spaces, the standard generally requires us to install in-rack sprinklers to compensate for the delayed system activation and the restricted water penetration. However, in palletized and solid piled storage, where installing sprinklers between the loads is not physically practical, the rules rely on flue spaces of less than 6 inches to starve the fire of oxygen and prevent vertical fire growth. Let us return to the second exception regarding design area reductions, which applies when the tables direct us to use extra hazard Group 1 or Group 2 densities. Under these conditions, we are permitted to reduce our design area by 25%, though we can never drop below a minimum of 2,000 square feet, provided we meet specific sprinkler criteria. We can apply this reduction in two scenarios. First, when using K8 high-temperature sprinklers for extra hazard Group 1, and second, when using sprinklers with a K factor of 11.2 or larger, regardless of their temperature rating. This means, for an extra hazard Group 1 density requirement, we can apply a 2,000 square foot design area by utilizing high-temperature K8.0 sprinklers or K11.2 sprinklers of any temperature rating. For an extra hazard Group 2 density, we can apply the same 2,000 square foot reduction by using K11.2 sprinklers with any temperature rating. When designing fire sprinkler systems for storage applications, we typically navigate two distinct concepts of clearance. The first is the minimum clearance, which applies to all CMDA, CMSA, and ESFR sprinklers to ensure the water discharge pattern is not obstructed. The second concept is maximum clearance. For CMDA sprinklers, we define this strictly as the distance between the top of the storage and the ceiling or roof deck, and it directly dictates how we approach our hydraulic calculations. But why does maximum clearance matter so much? The answer comes down to fire dynamics. When we have excessive clearance between the top of our storage and the ceiling, it takes longer for the heat to reach the ceiling and activate the sprinklers. During this delay, the fire grows significantly larger. Once the sprinklers finally activate, the water droplets are forced to fight their way down through a much stronger, faster-moving thermal plume just to reach the burning material. To prevent this from overwhelming the system, NFPA 13 establishes strict limits. For CMDA sprinklers, we must enforce a maximum ceiling clearance of 20 feet. But what happens if our actual ceiling is higher than this limit? We cannot simply ignore the gap. Instead, we are required to base our hydraulic calculations on a hypothetical storage height. We must mathematically increase our storage height in our design until the gap between this new hypothetical storage and the ceiling is reduced to exactly 20 feet. By increasing the storage height, our system is designed to discharge more water, giving it the power needed to overcome the challenges of excessive clearance. For example, if we have palletized, non-encapsulated Class 1 commodities with an actual storage height of 19 feet and a ceiling height of 45 feet, our clearance is 26 feet. Because this exceeds our 20-foot limit, we must design the system based on a hypothetical storage height of 25 feet. Looking at Table 21.2211, this means that instead of using the standard densities of 0.15 or 0.21 gallons per minute per square foot for high and ordinary temperature rated sprinklers, we must apply the higher densities of 0.20 or 0.28 gallons per minute per square foot in our design to overcome that extra distance. It is important to note that in certain situations, increasing the hypothetical storage height to maintain the maximum allowable clearance prevents the use of CMDA sprinklers entirely. For example, we know the maximum storage height for encapsulated Class 1 through 4 commodities is 20 feet. If the commodities in our previous example were encapsulated, the 25-foot hypothetical storage height would fall outside the scope of the standard. Therefore, CMDA criteria could not be applied, and we would need to follow alternative design approaches using CMSA or ESFR sprinklers. We can conclude that while many sections of NFPA 13 do not explicitly limit the ceiling height for CMDA sprinklers, the maximum clearance criteria inherently enforce a ceiling height limitation. Protecting palletized and solid-piled storage with CMSA and ESFR sprinklers is quite simple and straightforward. We primarily rely on design tables, and in our previous video, we reviewed exactly how to apply them. For CMSA sprinklers, Table 22.2 outlines the design criteria for Class 1 through 4 commodities, while Table 22.3 covers the criteria for Group A plastics. In these tables, the standard defines the K-factor, orientation, number of sprinklers in the design area, and minimum operating pressure based on the storage arrangement, commodity class, maximum storage height, maximum ceiling height, and system type. In these tables, although the design criteria for different commodity classes are listed in separate rows, the actual values are sometimes identical. For example, the design criteria for Class 1, 2, 3, and 4 commodities in palletized or solid-piled storage with a storage height of 30 feet and a ceiling height of 35 feet are exactly the same when using K19.6 sprinklers. For ESFR sprinklers, Table 23.3.1 outlines the design criteria. This table is similar to those for CMSA with one key difference. The number of sprinklers in the design area is not mentioned. According to Section 23.2.2, we should consider the 12 most hydraulically demanding sprinklers with 4 sprinklers on each of 3 branch lines. ESFR sprinkler design criteria are often identical across different commodities and storage methods. For example, using K14 sprinklers for a 20-foot storage height and a 25-foot ceiling requires the exact same design criteria for Class 1 through 4 commodities, cartoned Group A plastics, and exposed non-expanded Group A plastics, regardless of whether the storage is palletized, solid-piled, or racked. While this flexibility is a huge advantage, allowing a single ESFR system to protect a wide variety of goods regardless of the commodity or storage method, there is a catch. If we know for certain that a warehouse will only ever store lower hazard goods, like Class 1 commodities, using an ESFR system might actually result in a higher overall water demand. We'll explore exactly why this happens in the next section. Now that we understand the design rules, let's look at how our choice of sprinkler affects overall system demand. For this example, let's assume we are protecting a Class 4 non-encapsulated commodity. It's stored palletized with a 30-foot storage height under a 35-foot ceiling, and we are using a wet pipe system. Using CMDA sprinklers, Table 21.2.2.11 requires a design density of 0.57 gallons per minute per square foot. Multiplying this value by 2,000 square feet and ignoring minor and major losses results in a sprinkler system demand of 1,140 gallons per minute. Referring to Table 2015-2.6, which defines the hose stream allowances and durations for various system types, the required hose stream allowance is 500 gallons per minute with a duration of 120 minutes. Therefore, the total required system flow is 1,640 gallons per minute, necessitating a water tank capacity of 196,800 gallons. For CMSA sprinklers, Table 22.2 outlines using K19.6 pendant sprinklers at a pressure of 25 pounds per square inch. The design area requires 15 sprinklers. First, we calculate the minimum flow for each sprinkler. Then multiply that by 15 to find a roughly estimated total flow of 1,470 gallons per minute. Again, referring to Table 2015-2.6, the required hose stream allowance is 500 gallons per minute with a duration of 90 minutes. Therefore, the total required system flow is 1,970 gallons per minute, which means we need a water tank capacity of 177,300 gallons. For ESFR sprinklers, Table 23.3.1 specifies 6 design options based on K factor and sprinkler orientation. Selecting the highest available K factor yields the lowest required minimum operating pressure. Under these parameters, the minimum calculated flow per sprinkler is 112.7 gallons per minute. Multiplying this by the 12 sprinklers required in the design area results in an estimated base system demand of 1,352 gallons per minute. The required hose stream allowance is 250 for a 60-minute duration. Consequently, the total required system demand is 1,602 gallons per minute, necessitating a minimum water tank capacity of approximately 96,120 gallons. As demonstrated, using ESFR sprinklers reduces the system demand for this scenario. Now let's assume the commodity is Class 1. For a CMDA sprinkler system, the design density changes to 0.29 gallons per minute per square foot, and the sprinkler demand drops to 580 gallons per minute. The total demand, including the hose stream allowance, decreases to 1,080 gallons per minute, requiring a water tank capacity of 129,600 gallons. The demands for the CMSA and ESFR systems remain unchanged. In this scenario, the CMDA sprinkler system demand is lower than the other two types. Additionally, because the minimum flow of each CMDA sprinkler is significantly lower here, the required branch line pipe size will be smaller compared to CMSA or ESFR systems, which helps decrease the overall system cost. As these two examples illustrate, selecting the ideal sprinkler type depends entirely on the specific project variables. System designers must thoroughly evaluate the project parameters, account for the limitations of each sprinkler type, and use that data to design the most efficient and cost-effective system.